Now my clock has been running since 2.5 years, and I just wanted to give you a short update on its accuracy and some further progress. Since it started running 2.5 years ago, the clockwork has done 80 million beats with no visible wear of the wooden teeth and wooden bearings, and the tip of the pendulum has traveled half around the Earth. But I had not expected that regulating the compensation actually took me twice as long as building the clock. For regulating the clock, I used the excellent timegrapher by Dr. Henschke, which proved invaluably useful. This is the main unit. On top you can see the meteorologic sensor for air pressure, temperature and humidity. And it comes with an AC adapter, a GPS receiver as time standard, a receiver for the German radio time signal, and a fork light barrier to measure the pendulum transit. I cut it in half to fix it to my pendulum scale. After switching it on, it scrolls through all the settings, and there's a pot to choose and a button to start a measurement. The data are written to a micro SD card, but you can also read it out via Wi-Fi. The data are written in ASCII format, so you can easily paste them into Excel for further processing and to visualize them. Surprisingly, I had to build 3 different pendulums to get the temperature compensation right. First one was the inverted Mahler pendulum, which I already had explained previously. When it gets warm, the brass wires expand, lowering the brass balls to accelerate the pendulum. I had calculated it for full temperature compensation at a lever ratio of 1:9, but even if I screwed the balls out till the very end, it proved to be undercompensated. Originally, I had suspected too much friction in the joints of the rocker levers, but this was not the case. Second was a gridiron pendulum, very close to Harrison's original design. The gridiron, consisting of 5 iron wires and 4 brass wires, extended the maximum length from the suspension hook down to the pendulum bob, which would go here. To adjust the degree of compensation, I used Harrison's penny whistle design. By setting a pin in one of its holes, you can interconnect a span of brass tube to reduce the compensation. I had calculated it for 100% compensation at the top hole and plenty of holes below to allow a willful overcompensation. But even though I desperately drilled an additional hole down here, right above the bob, to disable the brass tube almost entirely, it still proved heavily undercompensated. In this measurement you can see that the ambient temperature in blue and the rate of the clock in orange look like vertically mirrored, so the clock was still way too slow when it gets warm. Third came an Inval pendulum. This rod is made from Invals 36, and the threaded brass tube rising above the bob allows stepless adjustment of the temperature compensation. And again the same story. Even at maximum, the clock was again undercompensated. Luckily, there was enough space left on the pendulum rod to add another 70 millimeters of rising brass tube below the bob. And only by this modification I finally got the compensation into the ballpark range. So there were 3 pendulums, 3 entirely different designs and different materials, and 3 times the same result of heavy undercompensation. After this, the probability of a design flaw or of wrong material properties is virtually nil. No, there must be a different cause. Harrison had postulated that the pendulum must be shorter when warm to achieve full barometric and temperature compensation. When it gets warm, the air gets thinner, causing a larger amplitude, and by means of the circular error, some slow running of the clock. To compensate this, a slight temperature overcompensation is desired. In the context of my own clock, however, a slight overcompensation was not sufficient. I needed way shorter when warm, an overcompensation almost by the factor of 2. But now I'm fine. For fine adjusting the compensation, I used the mean square error method. I calculated in Excel a model of the clock's rate out of the measured temperature and air pressure and compared it to the real measured rate. The coefficients of the model were then adjusted until the squared deviation between model and reality became minimal. Finally, I ended with coefficients of -4 milliseconds per day and Kelvin and of -11 milliseconds per day and hectopascal. With these settings, my clock came very close to Harrison's original claim of 1 second error in 100 days. It stayed within a bandwidth of 1 second for more than 2 months before it dropped out of the second. And this was maybe only because my apartment was not heated for 2 weeks during the Christmas holidays and the temperature dropped to 10 centigrades. All in all, that's an accuracy of better than 0.2 parts per million, which is by a factor of 10 better than most quartz watches. I am totally fine with this accuracy, being far better than I ever had expected from an hand-built plywood clock. After this, I removed the timegrapher again. The timegrapher had proved invaluable for adjusting the clock, but with it attached, the clock seemed to me like a patient subject to mistrust and constant surveillance. Without it, the clock got its pride back, now acting as the prime time base of my household.